As a co-organizer with Gerhard, we decided, before we move on to, actually the next session will be on experiments, getting onto experimental verifications and ideas. And I think at this time we decided to do an overview of all the problems that came up. And I think the last talk perfectly illustrated the different positions that are held. And we wanted to clarify around this question whether everybody agrees non-signaling is required to allow for the peaceful coexistence between non-locality and special relativity. And that very notion was the center actually of that last talk in criticizing that. But there's another solution that was, of course, always offered by hidden variables approaches and all that is, but if the signaling information is hidden and not accessible, whether that would save you. And I want to make that case. So what I want to say is the purpose of this talk is to provide in simple terms, and I will use visuals, conceptual illustrations, of a foundational overview of physical, metaphysical, epistemic principles, which are shared by deterministic ontological approaches to quantum mechanics, including emergent quantum mechanics. And we haven't really defined emergent quantum mechanics yet, so I want to spend some time on what do we actually mean by emergence, and how can it contribute to the developing emergent quantum mechanics. And employing the question posed in the title, I want to discuss key assumptions in relation specifically to the problem of superluminal signaling. Gerhard Grössing in his talk yesterday referred to that, because everybody in this room knows if you have a local deterministic theory and you want to account for EPR-type data, you have a huge problem unless you are working through a superdeterminist avenue, and I'm going to talk about that briefly. But if you believe in a free choice approach, there is a major problem, of course, and I think this was exactly what the last discussion was just all about. And I want to make clear as being an organizer and also a sponsor and research developer going ahead in the future, that we face the problems that we need to solve to actually have quantum mechanics be understood as an emergent phenomenon. And I don't know, I was highly skeptical 2 years ago about this approach, but the longer I think about it, I think we can actually do something about it. But experiments will be the test in the end. So the point is not to provide a solution to the problem. Obviously, I don't have one, and so nobody has one. But it's really to better define the problem and to have a more precise understanding in this community about what the problem is. The strategy of the talk is comparative. I will go back and forth between the orthodox interpretation and the propositions and claims by emergent quantum mechanics. And as you can see, the orthodoxy is colored green, for this is all right and we are safe there. And red, as a warning label, we should be very careful about what we claim when we do emergent quantum mechanics. So, this is about search for foundations, and I mentioned that today is, why the quantum, the big question. Everybody agrees, I think, in this room, that foundational approaches of any kind must be, in the end, be compatible with the non-signaling principle. Bell-type violations, EPR-type experiments, there's no question about the data, and I think this we should take as a starting assumption right now. Just two examples of approaches more from the mainstream perspective. Clearly, because of this requirement, there is work underway, since several years, since the 90s at least, to actually define the non-signaling principle as the foundational principle from which possibly a quantum formalism, at least partially, could be derived as a consequence. Like just Popescu and Röhrlich, I remember 94, that sort of paper. But also, of course, in the Seilinger group, the proposal in the 1990s, and the work is continuing, to use irreducible probabilistic information as a foundational principle in this foundational work to make sense of why the formalism is what it is. And so these are approaches more in the mainstream perspective. But of course, in the more alternative communities, historically, hidden variable theories were seen as a foundational ontic approach. And we know they work. At least they are a logical possibility when abandoning the locality assumption. That's why, under the assumption of non-locality, hidden variable theories are a logical possibility, even though they might not be distinguishable experimentally at all, might not have any different predictions. Recently, though, an emergent quantum mechanics, which belongs to the class of local deterministic theories, are widely being discussed and have created this interest. And here the question is, are these sort of theories are a logical possibility, and under what assumptions are they a logical possibility? And here I want to distinguish just briefly, these are all, again, free choice assumptions which include free choice and not superdeterminism. So I really want to limit it to that in this talk. Now, all of this, what they share, they are ontological approaches, of course, to quantum theory. What is the difference? Of course, orthodox mechanics, they are really state-of-knowledge theories. We've heard about this many times. Here, the mathematical object, called quantum state, is really a model representing a state of knowledge or information about a state whose true nature is undetermined and or unknowable, even in principle. In ontological quantum theories, e.g. emergent quantum mechanic approaches, the mathematical object called quantum state is a model of a real physical state whereby information points to an underlying ontic reality. That is what kind of is the shared assumption for local deterministic theories. We've heard that yesterday all the way through. Now, emergent quantum mechanics. It's interesting we haven't spent any time on defining what we mean by this, and I think it's time to just sum up some of the ideas. And also, I want to spend some time on what do we mean by emergence? Because not many, many of you are highly familiar with quantum theory, but really emergence theory is a whole other domain, and what are the connections, and what might be possible connections? So of course here, in quantum mechanics, the whole old debate about completion, incompletion is really sums up in the discussion about state of knowledge interpretations versus ontological state interpretations. And in emergent quantum mechanics, the idea is to ask the question, could progress be made towards developing an ontological theory of quantum phenomena by exploring connections between nonlinear emergent systems and quantum mechanics? Now, what is emergence? What are emergent structures, in the sense we're using it here? And interestingly, the same debate that goes on the last 80 to 90 years in quantum mechanics about the foundations of the theory or what the meaning of it, you find that same debate in emergence theory, complexity theory, chaos theory, supervenience theory. Is emergence really just a description, a state of knowledge about a complex system? Or, which is really supervenience theory, or is emergence, does it refer to a new ontological state that is irreducible in a causal sense? And that's really the meaning of strong emergence. And I want to explain what that means. So what are emergent structures? Please allow me, since nobody probably here knows my background a little bit, to show 2 slides what got me into this discussion. Since 25 years, I've been working on ideas connecting quantum coherence and emergent structures. And really pivotal to me was a meeting with Herbert Fröhlich as a postdoc in the 1980s, who of course always was interested in applying quantum concepts, even in macroscopic classical systems. And looking, what he recognizes, there's coherent states in both dimensions, at the classical level, at the quantum level, so can we learn something from this? And so I've really started working in his team. I've met with him, and my postdocs came from that research group. And this was all about finding commonalities between quantum and classical coherent states, especially, how do these long-range unpredictable correlations occur? And I was director at the Bioelectromagnetics Lab at Stanford University, which was an interdisciplinary research group, which lasted for 9 years. And there we did experiments, theory development, and computer simulations with a focus on quantum coherence and its connections to emergent dynamics and the flow of information in living systems. What came from this, I just want to say, I've stopped working in the laboratory, but you would call our work quantum biology today. In the 1990s, there was really not that word yet. But we worked on quantum entangled states in enzyme systems coupled to emergent processing. In 2000, that work was completed, culminating in a book, which I want to use the cover from that book, onto explaining to you the excitement of emergent structures. Because one, it's remarkable what local deterministic processes can do for you, even in the long range. So here's an example. At the lower level, living systems, the upper level, non-living systems. Typical spiral wave patterns that emerge in single cells or in social organization of dictyostelium slime molds. Of course, the familiar Belousov-Zhabotinsky reaction. This is a close-up shot of carbon monoxide oxidation on platinum surfaces. These are all driven systems with highly nonlinear interacting elements under boundary conditions giving rise to these states. And of course, the last 30 years has seen enormous excitement about those things. And there's many popularizations of that. What they share is that the mathematical description of all these, of the local processes for each of these systems, are partial differential equations that have the same nonlinear structure, thus giving rise to these similarities in these vastly different systems. And of course, the scales for these, go from spiraling arms of galaxies to hurricanes to millimeter-size structures all across. These are scale-free orders that emerge. Now, this is observed at the macroscopic global level. All this happens as a consequence of purely random interactions of the local elements at the microscopic level. And you get long-range correlations. They are unpredictable, yet they're completely deterministic. And here the puzzle is, and this is why it's unresolved, it's a very similar problem as in quantum theory, how to get from local random microscopic interactions. And of course, randomness here is deterministic. It's not irreducible randomness. Let's never forget that in this discussion. And how do we get to these emergent macroscopic structures? And there's three types of approaches that people think about. What's the kind of causality in the system? What is connecting this emergence of this information with the underlying order? What we're looking for is really a relational continuum, how to connect those two levels without necessarily reducing one to the other. And on the one hand, you have these events here, you have the emergent structure, and of course, what you would first assume is that you have a bottom-up causality happening, meaning you can fully reduce the observation of the higher order phenomena to just local interactions at the local reductionist level. And that most people share that view, and that's known as weak or epistemic emergence. It's also known as theory emergence, that your theory needs to have higher order descriptions, but really the ontology underneath this is purely reductionistic. And that goes under the term of supervenience, and it's an artificial word. There's no good translation into German, but it's basically about global emergent structures. They supervene on local processes, completely described by reductionism. And so that is uncontroversial, and that's sort of the mainstream interpretation of this. On the other hand, there is the view sometimes, when you hear about emergent structures, about top-down causality. Right? People equate very often self-organization systems and saying, oh, but what's great about it, what's unique about it is there's actually a cause coming from another plane acting down on the local elements, and that sounds quite mystical. And it is, because that's not emergent. And I think that's very often very misrepresented. This would be more Aristotelian formal causation. Thank you. It's scientifically untenable because there's an area of coming from up, and where should it come from? But there's a third alternative, and Gerhard Grössing referred to that yesterday, and that's bottom-up causality combined with top-down causality. We know this as feedback cycles, basically, where the boundary condition given by a global parameter actually acts on the local events, and in turn the local events are stabilized by that, but in turn they create the global state, and so there is no good word for that. So we use the word relational causality because it relates, in a causal sense, at least descriptively, those both levels. And this is what is called strong or ontic emergence, and also more in the terms as physical emergence. And in here, especially, the relationship between information, that emerging information, and the causal processes responsible for it, are a big question, and there are wide debates. And if you go to those conferences on these topics, it's an unresolved issue, and you have all different kinds of positions. Very much like the debates sound like on some of the foundation in quantum mechanics. So what in addition happens is that emergent states exist in a nested hierarchy connecting different organization level. So for example, a local element in one emergent structure can itself be an emergent structure, and so on, going up and down all the way. So we can speak of a scale-free relational continuum. So when you make an observation of an emergent state at one level, you must always be aware there's a higher level up and a higher level low. And so it is really a vast continuum, and so we don't know how far we can take this. But one implication is, before I say that, there's really two ways, I think, so far in this talk, how we can, in which way emergence may be important. Theory emergence, This would be almost, in relationship to quantum theory, would be analogical quantum modeling. These would, mentioning the experiments by Yves Coudet, where you have emergent classical properties which appear to be analogous to genuine quantum properties. And the way you could describe this is an analogy to quantum states, and that would be theory emergence. What we mean here, though, for some speakers in this conference, a much more radical proposition, physical emergence, in relation to ontological quantum modeling. The question is, could quantum states actually be emergent states in reality dynamically arising from a subquantum medium? And I think that has been a theme also yesterday as part of the possible backgrounds. So, how would this look? The quantum state would be an emergent quantum structure. This would be the microscopic level, submicroscopic interactions arising from a potential subquantum medium, and this would be described by strong and ontic emergence, by quantum emergence through relational causality. What this subquantum medium might look like, people speculated about this yesterday, could some form of zero-point energy, granular discrete space-time, and so on. I mean, not much is known about that, but certainly ZPE exists as a physical reality. So what you have, again, the possibility when you have a quantum emergent model that you have, just like in the classical case, long-range correlations which are unpredictable yet completely deterministic. And can you build an ontological quantum theory on that foundation? Again, here, of course, the relationship of information and causality is as open, a wide open topic. And we, at the Fetzer Franklin Fund, are very interested in that relationship and exploring that. So, coming back to this discussion at the end of the last talk, the orthodox view, of course, says that a strongly emergent quantum mechanics just simply should be impossible. Bell's theorem, instantaneous non-local correlation, EPR-type experiments, intrinsic quantum randomness, objective indeterminism, and finally, that culminates, that all these converge in the non-signaling principle, that signaling is not allowed. That means there must be irreducible non-randomness operating at the fundamental level, and that, of course, is not compatible with any emergent model. So, just two key findings from EPR-type experiments, the orthodox. On the one hand, we observe non-local correlations, and we say that they're completely non-determinist. And this unifies in the concept of non-signaling correlations, and we say because they're non-signaling, we have the peaceful coexistence between special relativity and non-locality. Emergent quantum mechanics would say, has a huge problem with that, right? How could all these be accounted for by a deterministic theory? Not. It seems to be a logical impossibility. So, because the non-signaling principle must remain intact. So I want to say, I want to take them the road. What is the option we have here? The non-signaling principle, everybody knows. I just want to say it's about the prohibition of superluminal information transfers between locations A and B. But, of course, the non-signaling principle does not prohibit superluminal non-signaling influences across space-like distances because we observe those in the EPR-type experiments. So clearly, whichever way you take, a problem of 21st century physics is to ask what kind of space-time structure allows for superluminal non-signaling influences. Whether you're in the mainstream or more alternative approaches, that is a shared problem. The question is whether emergent quantum mechanics can make a contribution to that, or whether, in the orthodox interpretation, we just must say, this is outside space-time, we can't access that problem. We have to remain at the descriptive level. Maybe there's other pathways, we can have a more realistic interpretation of the non-signaling criteria. And, for example, proposals like is space-time itself emergent structure, and so on. So, what do we actually see in EPR-type experiments? What is the phenomenology that we try to explain by all those various approaches? Non-local correlations in emergent theory actually are long-range informational correlations. Non-determinist correlations are not non-determinist, they are unpredictable informational correlations. So, Alice and Bob, and they look at their data, in the experiments, in EPR-type experiments, and this is an ideal scenario. And so there's, in this case, perfect correlations. And of course, the orthodox approach would say they're completely indeterministic events, they're random. for real. And of course, in emergent quantum theory, we have to assume that they're somehow deterministic, correlated, pseudo-random, and that was the point of the last discussion. Could there be a fine structure in these sort of data if you make some long-term experiments and so on and so on? I don't want to get into that. The point I want to make is that there's two kinds of metaphysical assumptions that are competing. The one is ahistorical, because in genuine indeterminism, there is no historical correlation between any of those detection events. And of course, in deterministic approaches, there must be historical correlations. This is experimentally a non-decidable question. If you just take the philosophical, metaphysical approach to this, you have to agree if you think it through. There is no analytic technique to prove that. There's no experiment you can come up with to actually decide one over the other. And that is well known. Now, I want to present the phenomenology in the following way. Here's the data, observed in the different local settings. Space-like, they're highly correlated, but phenomenologically, they are really long-range correlations. And they're unpredictable. That is seen in the laboratory. Now, in this plane of, this is what we see. This I call the plane of observation. Now, is there an ontic reality underneath this, which gives rise to these long-range unpredictable correlations? Of course, the early proposal said, the hidden variables program said yes. Of course, the orthodox program says no, there can't possibly be. All we need is the quantum formalism, and it's descriptive, it's purely epistemic. There is no ontic dimension to this. And this is, as I said before, for free choice models. Of course, in super deterministic approaches, where you have initial entanglement of states, involving time, you have no problem with long-range correlations. Because you don't need to make a choice. It is the laws of nature are deterministic, and these problems actually don't come up. And I want to just summarize why. There's two options. There's the deterministic theory, and there's super deterministic ones. Deterministic theory is coupled to free observer choice, of course, and in super deterministic theories, we couple it to lacking observer choice. The first one has the problem, of course, of superluminous signaling right away, and I think this was the last discussion. Of course, these theories do not have that problem. And I will not get into this here. I will stick only to this problem. So, the non-signaling principle and superluminal influences. Superluminal influences are allowed if they cannot, this is the orthodox position, cannot be used for signal transfer. Why? Because causal pathways simply don't exist. No problem. So this I call fundamental or ontological non-signaling. The alternative, and this is the approach chosen by, also I just see Professor Girardi saying this. You wrote about this, but John Holland in his book from 20 years ago, and also David Bohm wrote about this. The reason non-local hidden variables can work, because we have no access to the information. And this is exactly what I call epistemic non-signaling. And here it is that superluminosities are allowed if they cannot be used for signal transfer because of inaccessibility of information, which is associated with existing causal pathways. There's two options: inaccessibility to practical reasons or inaccessibility to theoretical reasons. And this I call phenomenal or epistemic non-signaling. And the question is, that was asked in the title was, is it enough to have non-signaling at the phenomenal or epistemic level only to obey the non-signaling principle, or, which I call phenomenal non-signaling, or must the processes that underlie the observed phenomena at the microscopic level actually be non-signaling? So it's really a juxtaposition of the epistemic and the ontic option. And I think not much work has been done on that. And I think we should really start looking at this in more detail, because the community working on the local determinist program is actually using this argument a lot of phenomenal epistemic non-signaling to keep the integrity of the non-signaling principle intact. Now, is the non-signaling principle a foundational principle? Can that be decided? Let me give an analogy on how to think about a phenomenal or epistemic non-signaling. Look at this. Imagine you have a physical channel capable of exchanging encrypted information between A and B. The key is destroyed and lost, and is inaccessible to any possible observer, past, present, and future. The question is, Was information actually transferred from A to B? Was there a causal flow? Is this even a decidable question? And unless you can decide that sort of problem, it's just an analogy. I don't know how far we can take this, but it's a good Gedanken experiment to start out from. Is the non-signal principle foundational or epistemic? We have no way right now to decide this. And I think there's lots of debates on this out there. And I just want to bring this up as an idea on how to think about this. Because does information depend on an observer? Or is information ontological? Does it exist independently? Could that question ever be decided? What I'm saying is, until this question is decided, whether the non-signal principle is foundational or epistemic, we can't say whether epistemic non-signaling is enough to protect the integrity of the to allow the peaceful coexistence of locality and relativity. Now, it's interesting if you look in the literature, and I've just done it in the past weeks, the argument for genuine intrinsic indeterminism and genuine non-signaling often ends up in circular reasoning. You find statements like, because of the non-signaling principle, the observed unpredictability of non-local correlations must be due to intrinsically random, i.e. objectively indeterminate events. At the same time, just a few pages later, you find a statement, because of the unpredictability of non-local correlations is the result of intrinsic quantum indeterminism, these must be non-signaling. And so it's clearly, in my view, if I look at the literature right now, and I have not dug too deep into it, so I'd like to get your feedback on this. At present, I believe it remains unclear whether the non-signaling principle could be a foundational or must remain an epistemic principle. And I don't even know what kind of experiment to do to decide on that. But until we can decide on that, I think all these issues about whether local deterministic theories remain possible or not are unresolved, an open question completely. So, 2 last slides, if I have. Okay. So this is the question we started out with. Does epistemic, or I call it phenomenal non-signaling as well, ensure the peaceful coexistence of special non-locality? This is the conclusion. In order for epistemic non-signaling to be valid, I think, this is what we say, as an argument, the non-signaling principle itself must, of course, be epistemic only. It cannot be foundational. However, as said before, efforts are now underway arguing that the non-signaling principle might be a foundational principle for orthodox quantum mechanics. If that were shown, of course, then the argument from inaccessibility to information could no longer guarantee the peaceful coexistence, at least in free choice models, and it would show the impossibility of local deterministic theories which include free choice. So this is what this sums up. But what is interesting is, to me, it seems rather ironic that orthodox quantum mechanics, which is a state of knowledge theory, i.e. not ontological, would require the non-signaling principle to be foundational, even ontic, in order to refute the logical possibility of an emergent quantum mechanics. I find that really interesting. I don't know if it's true, but I just want to throw out these ideas and get your feedback on this. So to me, one of the most interesting questions going forward, and I think in the Vienna group for sure, this is one of the most interesting questions as well here, is what is non-signaling information? Option 1, is it something real, i.e. ontic? Or is it merely an epistemic construct useful in predicting measurement outcomes? And it's all in here. And the question is this experimentally decidable or not? What are the arguments for and against? Because if you say information is ontological, then you ontologize your theory. But if you remain in the realm of non-signaling information being an epistemic construct, then you continue to allow the logical possibility of an emergent quantum mechanics. Thank you very much.
Thank you, Jan. We still have time for a few questions. Andre?
At the very beginning, you mentioned this very popular now approach of Bruckner and Seilinger, based on irreducible quantum randomness.
Yes.
And according to your classification, it is not emergent theory, or?
It's not.
It's not.
No.
Why? Because it's primitively not, if you reduce to classical ensemble randomness. But why you cannot exclude that there exists some more general theory which we have no idea? I just remind you that we don't have strict mathematical definition of classical random sequence. There were attempts by Kolmogorov, complexity,
that's
and
my
so
point.
on.
I agree with you.
So maybe it would be some view to randomness which would imply irreducible randomness and classical. So why are you so strict that it's the end of the story? Yeah?
Because, no, I totally agree with you that we have no criterion to decide true randomness to determine whether time series are truly random or not. The point is, as I said from the beginning, this is emergence theory, and that's where I'm coming from in my profession, is a fully deterministic theory. And what you're proposing is to insert indeterminism into emergence. And that is, we can think about that, but that's not what emergence theory is as we know it. And I think it would be completely, you would come to, I don't see any possibility for this. Because if you have true indeterminism in these theories would be completely ahistorical. There would be no memory. And emergent structures do require memory. They're completely historical processes.
Well,
I think, and then Howard.
Is there somebody else?
Yes, no, that's okay.
Well, the very, very short question. If you have an epistemic theory from this point of view, but the theory can be relativistically generalized, for instance, as people did, Professor Haile first, and then Dürr and Zanghi, you generalize it in such a way that you have a fully relativistic theory, however, with the hidden preferred reference frame. Would you claim that there is peaceful coexistence with relativity?
I didn't touch on the solution through relative, exactly.
I think then there's Howard. Howard, you still want to ask the question? He had his hand up first.
Thanks. Thanks for that. This is just a terminological point. In my mind, signaling is an operational concept which refers to agents and whether or not information can get from one to another. So I don't think it's an appropriate word to use for microscopic information, microscopic superluminal causal transfer or whatever you like. So you seem to I can't remember exactly what the terms were used, but...
You're absolutely right. That's why I'm saying that the relationship between causality, the causal microscopic process, to what we call information, I say is unresolved. I think this is, if you go to philosophy conferences on the relationship of causality to informational processes, it's a wide open question there for sure. And so that was my question at the end, in this encrypted message analogy, was the information actually being transferred or was there causal flow? That's why I posed both of these. Because you have to address both of these together.
I understand. I guess I'm just saying that I think maybe you should restrict the term signaling to something involving agents.
Well, signaling coming from biophysics. We talk about signaling all the time without agents. And so they are causal signals. But you're right. The regular definition with signals is the choice of agents choosing to communicate information. So I do get that. But it's also, I want to leave it open still.